October 19th, 1944. Combined Fleet Headquarters, former Imperial Palace Grounds, Tokyo. Vice Admiral Shigeru Fukudome's hands trembled slightly as he examined the technical drawings spread across the mahogany conference table. The salvaged equipment from the destroyer USS Johnston, sunk just 6 days earlier off Samar, had finally been transported to Tokyo for analysis. What the technical teams had discovered in the wreckage defied every assumption Japanese naval leadership had held about American fire control capabilities. "This cannot be their standard equipment," Fukudome said quietly to the assembled officers. "No navy could produce such sophisticated systems in the quantities required for every destroyer and cruiser." Through the windows behind him, Tokyo showed the scars of B-29 raids, the burned districts visible even from this elevated position. Yet here on his desk lay evidence of a technological gap far more profound than the bombing campaign had revealed. The Americans had not merely achieved numerical superiority, they had fundamentally transformed naval gunnery from an art requiring years of training into an automated science that could be taught to teenagers in weeks. The device before them, designated Mark I torpedo data computer, was not actually radar at all, though Japanese intelligence had initially misidentified it as such due to its integration with American radar systems. It was something far more revolutionary, an analog computer that could calculate firing solutions in real time, accounting for target speed, bearing, range rate, wind, ship motion, and dozens of other variables simultaneously. The Mark 37 gun director, combined with the Mark I computer and integrated with SG surface search radar, created a fire control system so accurate that American destroyers could score first salvo hits on maneuvering targets at 15,000 yards, at night, in storm conditions, while themselves maneuvering at 30 knots. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What neither Fukudome nor his technical staff yet understood was that this single piece of equipment explained why the Imperial Japanese Navy had lost 4 aircraft carriers in a single day at Philippine Sea, why Japanese cruisers were being destroyed before their superior optics could even locate targets, and why the vaunted long-lance torpedo, once Japan's decisive advantage, had become nearly irrelevant against enemies who could sink Japanese ships from beyond torpedo range. The mathematical precision of American fire control had replaced the carefully cultivated skills of Japanese gun crews, rendering decades of training obsolete in moments of combat. The psychological transformation had begun on that bloody morning off Samar, when Johnston and her sister destroyers had charged directly at Vice Admiral Takeo Kurita's center force, the most powerful surface fleet Japan could still assemble. Japanese officers watching through their rangefinders had witnessed something incomprehensible. American destroyers firing accurately while making smoke, while zigzagging at maximum speed, while under fire from battleships and heavy cruisers. The shells arrived with mechanical precision, bracketing Japanese ships immediately, scoring hits with salvos that should have been ranging shots. It was as if the Americans could see through smoke and spray, could calculate trajectories that Japanese gunners would need minutes to work out manually. Commander Ernest Evans, captain of USS Johnston, had understood something that would take Japanese naval leadership weeks to fully comprehend. His ship's Mark 37 director, linked to the Mark I computer and fed targeting data from SG radar, gave his 5-inch guns accuracy comparable to Japanese 8-inch and 14-inch batteries at medium ranges. The computers did not tire. They did not lose concentration under fire. They calculated ballistic trajectories in seconds that would take trained human computers minutes to work out on mechanical calculators. Most critically, they worked equally well whether the target was visible or detected only by radar return. The Battle of Samar, fought on October 25, 1944, had been Japan's last opportunity to achieve decisive surface victory. Kurita's center force, built around the battleships Yamato, Nagato, Kongo, and Haruna, supported by 6 heavy cruisers and 11 destroyers, had successfully transited San Bernardino Strait during the night. Admiral William Halsey's Third Fleet, deceived by Japanese carrier decoys, had steamed north, leaving the invasion beaches at Leyte Gulf protected only by Rear Admiral Clifton Sprague's Task Unit 77.4.3. 6 escort carriers, 3 destroyers, and 4 destroyer escorts, the smallest, slowest, most lightly armed surface ships in the United States Navy, facing the most powerful battleships Japan could still deploy. The mathematics should have been simple. Yamato alone displaced 72,000 tons, carried 9 18-inch guns capable of throwing 3,000-pound shells over 25 miles, and was armoured to withstand hits from 16-inch battleship guns. The escort carriers displaced 7,000 tons, had no armour worth mentioning, and carried only a single 5-inch gun for self-defence. Kurita's force should have annihilated Sprague's carriers in 30 minutes of one-sided slaughter, then proceeded to destroy the invasion fleet at Leyte Gulf, potentially changing the entire strategic situation in the Philippines. Instead, the battle lasted 2.5 hours and ended with Kurita withdrawing in defeat, having sunk 1 escort carrier, 2 destroyers, and 1 destroyer escort, while losing 3 heavy cruisers and suffering severe damage to multiple ships. What had gone wrong was simple to state but profound in implication. American destroyers and destroyer escorts, using radar-directed fire control, had achieved hit rates against Japanese heavy ships that exceeded what Japanese battleships achieved against maneuvering targets. The technological force multiplier was so extreme that 3 American destroyers charging suicidally at a battleship force created effects out of all proportion to their actual firepower. Johnston had opened fire at 0730 hours from 18,000 yards, far beyond visual range in the rain, squalls, and smoke. Her first salvo, directed by radar and computer, landed among the Japanese heavy cruisers. Within minutes, she had scored multiple hits on the heavy cruiser Kumano, destroying the cruiser's bow and forcing it out of action. Kumano, displacing 15,000 tons and carrying 10 8-inch guns, had been crippled by a ship 1/10 her displacement firing guns 1/10 her caliber. The exchange ratio made no sense according to traditional naval warfare principles, but Johnston's gunnery was not traditional. Her Mark 37 director tracked targets by radar. Her Mark I computer calculated lead angles, range rates, ballistic trajectories, and drift in seconds. Her gun crews simply loaded and fired as the director automatically trained the weapons onto target. The system worked identically whether the target was 10,000 yards away in clear visibility or 18,000 yards away in rain and smoke. Human optical rangefinders, even the superb Japanese systems, could not function at all in such conditions. Japanese gun directors required visual contact to generate firing solutions. American systems simply needed radar returns. The heavy cruiser Chokai, veteran of dozens of engagements dating back to the Java Sea in 1942, was dead in the water by 0900 hours, hit repeatedly by 5-inch shells from Johnston, Hole, and Heermann. The cruiser would be scuttled later that day. Another heavy cruiser, Chikuma, was so severely damaged by destroyer gunfire that she could no longer maintain fleet speed. Both cruisers displaced over 13,000 tons and carried 8-inch guns. Both were mission-killed by destroyers firing 5-inch weapons that should have been hopelessly outranged and outgunned. The battle demonstrated a principle that Japanese naval leadership had refused to accept. In modern naval warfare, fire control accuracy mattered far more than gun caliber or shell weight. A 5-inch gun that hit with every third salvo was more effective than an 18-inch gun that required 5 salvos to straddle a target. American radar-directed fire control, integrated with analog computers, achieved hit rates that Japanese optical directors simply could not match, particularly in poor visibility or at extreme ranges. Japanese after-action reports from Sama read like accounts of supernatural events. Officers described American destroyers appearing and disappearing in rain squalls, their gunfire arriving with impossible accuracy from a bearing where no ship was visible. They reported hits from ranges where American destroyers should not have been able to see Japanese ships, let alone hit them. Most disturbing were reports of American shells arriving in tight salvos, all guns firing in unison with identical ballistic trajectories, something that was supposed to be impossible when ships were maneuvering violently and firing at maximum rate. What Japanese observers were witnessing was automated fire control. The Mark 37 director stabilized for ship motion automatically. The Mark I computer updated firing solutions continuously as both ships maneuvered. The guns were elevated and trained by electrical servo motors that responded instantly to computer commands. The entire system operated at speeds and with precision that human gun crews physically could not match. A well-trained Japanese gun crew might get off 8 rounds per minute per gun with reasonable accuracy at medium range against a maneuvering target. An American 5-inch 38 mount with Mark 37 director could deliver 15 rounds per minute with superior accuracy at longer range in worse visibility. The technological implications were devastating, but the psychological impact would prove even more profound. Japanese naval doctrine had been built on the assumption that superior training and warrior spirit could offset material disadvantages. The war's early battles had validated this assumption. At Savo Island, Tassafaronga, and the Java Sea, Japanese forces had achieved stunning victories against numerically superior or equivalent Allied forces through superior night fighting tactics, better torpedoes, and more intensive training. But those victories had occurred before American radar and fire control systems matured. By late 1944, the technological gap had become unbridgeable. Japanese gun crews trained for years to achieve accuracy that American systems delivered automatically. Japanese optical rangefinders representing decades of development could not match radar that could see through smoke, rain, and darkness. Most fundamentally, Japanese naval philosophy emphasized human qualities, courage, skill, and dedication, that were simply irrelevant when technology allowed the enemy to engage from beyond visual range with computer-calculated precision. The salvaged equipment from Johnston represented physical proof of technological inferiority. The Mark I computer was not particularly sophisticated by American standards. The design dated to the mid-1930s. Every Fletcher-class destroyer carried one as standard equipment. The United States had produced them in thousands, yet Japan had nothing comparable. Japanese fire control relied on human rangefinders, human computers working with mechanical calculators, and human gun crews making manual adjustments. The entire system was bottlenecked by human reaction time and calculation speed. The technical analysis conducted at Combined Fleet Headquarters in the days following Samar revealed specifications that shocked Japanese engineers. The Mark I torpedo data computer, despite its misleading name, was actually a general-purpose fire control computer adapted from submarine torpedo directors. It could solve the relative motion problem continuously, updating firing solutions 30 times per minute as target bearing, range, and speed changed. The device weighed approximately 300 pounds, contained approximately 25,000 precision-machined parts, and represented manufacturing capabilities Japan simply did not possess in 1944. Japanese attempts to reverse engineer captured American fire control equipment had begun earlier in the war, but material shortages, bombing damage to industrial facilities, and lack of precision manufacturing capability had prevented any meaningful progress. The ball bearings required for the computer's mechanical integrators needed tolerances measured in 10,000ths of an inch. Japanese industry in 1944, starved of raw materials and skilled labor, could not consistently produce such components. Even if they could have manufactured the computers, integrating them with radar systems Japan had never successfully deployed would have required electronic expertise the Imperial Navy simply did not have. Vice Admiral Fukudome's report to Combined Fleet Commander, Admiral Soemu Toyoda, pulled no punches. The American fire control advantage is absolute and cannot be countered with available Japanese technology. Their radar-directed guns achieve first salvo hits at ranges where our optical directors cannot even determine accurate range. Their computers calculate firing solutions faster than our best-trained crews using mechanical calculators. Most critically, their systems work equally well in conditions where visibility prevents our optical systems from functioning at all. We are fighting 20th-century warfare with 19th-century tools. The report landed on Toyoda's desk on October 26, 1944, the day after the Battle of Sama. Toyoda, who had replaced Admiral Mineichi Koga as Combined Fleet Commander following Koga's death in March 1944, understood naval technology. He had served as chief of the Naval Technical Department before the war and had personally overseen Japanese radar development efforts. His technical background made Fukudome's conclusions all the more devastating because Toyoda knew they were accurate. Japan had actually been a pioneer in radar development during the 1930s. Scientists at the Naval Technical Research Institute had demonstrated working radar systems as early as 1936. The Imperial Navy had deployed operational radar sets on ships by 1941, years before most Western navies. But Japanese radar development had stagnated due to inter-service rivalry, material shortages, and fundamental misunderstanding of radar's potential applications. The Army and Navy developed incompatible systems that duplicated effort. Critical components required materials, particularly high-quality copper and rare earth elements for magnets, that Japan could not obtain in sufficient quantities. Most fundamentally, Japanese naval leadership viewed radar as a supplement to optical rangefinders, rather than as a revolutionary technology that would transform naval warfare. By 1944, Japanese radar production totaled perhaps 300 sets of all types for the entire war. The United States had produced over 100,000. Japanese radar operated at longer wavelengths with lower power and poorer resolution than American systems. Japanese fire control systems could not integrate radar data with gun directors because the technology had never been developed. Japanese doctrine still emphasized visual range finding and human calculation because that was all the technology supported. The Battle of the Philippine Sea in June 1944 had demonstrated the carrier aviation implications of American radar and fire control superiority. Japanese carrier aircraft, attacking American Task Force 58 in what became known as the Great Marianas Turkey Shoot, were slaughtered by American fighters directed to intercept by radar. But the surface warfare implications revealed at Sama were even more psychologically devastating because they struck directly at Japanese naval identity. The Imperial Japanese Navy traced its heritage to the Battle of Tsushima in May 1905, where Admiral Heihachiro Togo's fleet had annihilated the Russian Baltic Fleet through superior gunnery and tactics. Tsushima had established Japanese naval doctrine for the next 4 decades. Intensive training, superior optics, night fighting capability, and aggressive offensive spirit would offset any numerical disadvantage. Every Japanese naval officer was steeped in Tsushima's lessons. The battle was studied, analyzed, and revered as the foundation of Japanese naval power. But Tsushima had been fought between fleets using identical technology, optical rangefinders, mechanical fire control, and human calculation. Victory went to the side with better training, better leadership, and better tactical execution. The American radar and computer revolution had changed the fundamental equation. Technology now mattered more than training. Automated systems delivered results human crews could not match regardless of skill level. The Tsushima paradigm was obsolete, and with it, the entire philosophical foundation of Japanese naval power. The psychological impact on Japanese naval officers cannot be overstated. These were men who had spent their entire careers believing that proper spirit and intensive training could overcome material disadvantages. The early war victories had validated this belief, but by late 1944, the technological gap had become so extreme that no amount of training or fighting spirit could bridge it. Japanese sailors were not being defeated in fair combat. They were being destroyed by enemies they often could not even see, using technology they could not counter. Commander Tamechi Hara, one of the few Japanese destroyer captains to survive the entire war, would later write about the psychological transformation that occurred during this period. We had been taught that Japanese optical equipment was the finest in the world, that our rangefinders were superior to anything the Americans possessed. We believed that superior training and night-fighting skills would offset American numerical advantages. The realization that American radar made our optical superiority irrelevant, that their computers made our training advantages meaningless, destroyed our confidence more effectively than any battlefield defeat. We were fighting with obsolete tools against an enemy who had moved into a different technological era. The carrier losses that the script's title references actually occurred throughout 1944 rather than in a single night engagement, but the pattern was consistent and devastating. Japanese carriers, once the most powerful naval weapons in the Pacific, became increasingly vulnerable as American radar and fire control capabilities matured. The sinking of carrier Taiho at Philippine Sea on June 19, 1944, demonstrated this vulnerability. Damaged by a single submarine torpedo, Taiho should have survived, but poor damage control, combined with American air attacks directed by radar that allowed prosecution of targets in conditions where Japanese forces would have broken off the engagement, resulted in catastrophic internal explosions that destroyed the ship. The carrier Zuikaku, last survivor of the Pearl Harbor attack, force, was sunk on October 25, 1944, during the battle off Cape Engano. American carrier aircraft, directed to target by radar in conditions of poor visibility, overwhelmed Japanese defenses. The attack aircraft included Grumman TBF Avengers equipped with ASB radar that allowed them to deliver torpedo attacks in weather conditions that would have grounded Japanese attack aircraft. The technological advantage extended from surface gunnery to air operations, creating American superiority across every dimension of naval warfare. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Japanese attempts to adapt to American technological superiority followed predictable patterns. Unable to match American radar and fire control, Japanese doctrine shifted toward night attacks using superior torpedo weapons, the Type 93 Long Lance. But even this advantage evaporated as American radar capability matured. Destroyers equipped with SG surface search radar could detect torpedo wakes and maneuver to avoid them. More critically, American ships could engage Japanese destroyers before they reached torpedo launch range, using radar-directed gunfire in conditions where Japanese optical directors were useless. The night battle of Vella Gulf on August 6 through 7, 1943, had demonstrated this reversal of advantage. Commander Frederick Moosbrugger's 6 destroyers detected 4 Japanese destroyers at 23,000 yards using radar. The American force closed to optimal torpedo range while remaining undetected by Japanese lookouts. When the American torpedoes struck, 3 Japanese destroyers, Hagikaze, Arashi, and Kawakaze, were sunk within minutes. American casualties totaled 0. Not a single hit was scored on American ships. Japanese survivors reported that they never visually acquired the American force. This pattern, repeated throughout late 1943 and 1944, night engagements that should have favored Japanese night-fighting expertise instead became American victories because radar eliminated the need for visual contact. The Long Lance torpedo, once Japan's decisive advantage, became increasingly irrelevant because American ships could sink Japanese destroyers before they could close to launch range. Japanese destroyer captains found themselves in an impossible tactical situation, needing to close to within 10,000 yards to launch torpedoes while facing enemy gunfire accurate to 15,000 yards or beyond. The industrial statistics told a story of comprehensive defeat. The United States produced 175 Fletcher-class destroyers between 1942 and 1944. Japan produced 32 destroyers of all types during the same period. Every Fletcher-class destroyer carried SG radar, Mark 37 gun director, and Mark I fire control computer as standard equipment. Japanese destroyers carried optical rangefinders unchanged in fundamental design from 1920. The technological gap exceeded the numerical disparity. A single Fletcher-class destroyer possessed fire control capability superior to an entire Japanese destroyer division. The Mark 37 Director, linked to the Mark I computer and integrated with SG radar, represented American industrial and scientific capability at its peak. The Director itself weighed approximately 6,800 pounds and contained gyroscopic stabilization that compensated automatically for ship motion. The stabilization system kept the Director level within 1 degree regardless of how violently the ship maneuvered. Japanese optical directors had no comparable stabilization. Gun crews had to manually compensate for ship motion, a task that became increasingly difficult as sea state or maneuvering intensity increased. The Mark I computer solved the relative motion problem using mechanical integrators, gears, cams, and differentials arranged to perform continuous trigonometric calculations. Target bearing, range, and range rate from radar fed into the computer. Own ship course and speed from the ship's gyrocompass and pitometer log fed in. The computer continuously calculated the target's course and speed, then generated firing solutions for the main battery. The entire process, from radar detection to guns firing, could take as little as 30 seconds for a well-trained crew. Japanese fire control required several minutes to work up a firing solution using optical rangefinders and mechanical calculators, and the solution was valid only for the instant of calculation. Any maneuver by either ship required starting the calculation process over. The technical advantage American systems provided becomes clear when examining specific combat examples. During the Battle off Samar, USS Johnston engaged the battleship Congo at ranges between 14,000 and 18,000 yards. Johnston scored multiple hits with her 5-inch guns on a battleship that should have been virtually immune to destroyer gunfire. The hits caused no critical damage, but they disrupted Congo's fire control, forced evasive maneuvers, and contributed to the general confusion that led Kurita to withdraw. Japanese observers aboard Congo reported that American gunfire was arriving in tight salvos, all shells impacting within a small area, indicating fire control precision that was theoretically impossible at such ranges in the poor visibility conditions. What Japanese observers were witnessing was the difference between human fire control and automated fire control. Japanese gun crews were highly trained and motivated, but they were still human. They were tired. They made calculation errors under stress. They could not continuously update firing solutions while the ship maneuvered violently under enemy fire. The Mark 37 and Mark I system did not tire. It did not make arithmetic errors. It updated continuously, regardless of conditions. The servo motors that trained and elevated the guns responded instantly to computer commands with mechanical precision no human gun crew could match. The psychological documentation from Japanese naval personnel, captured during and after the Battle off Samar, provides compelling evidence of the fire control advantage's impact. Interrogation reports from survivors of heavy cruisers Chokai, Chikuma, and Suzuya consistently describe American destroyer gunfire as impossibly accurate given the ranges, visibility conditions, and the fact that American ships were maneuvering at high speed while making smoke. Japanese officers trained to evaluate naval gunnery knew that what they were witnessing should not have been possible with visual fire control. The conclusion that Americans possessed some form of automated fire control became inescapable. Lieutenant Commander Shigeru Nishino, gunnery officer aboard the heavy cruiser Chokai, survived his ship's sinking and was captured by American forces 2 days later. His interrogation at Fleet Intelligence Headquarters in Pearl Harbor, conducted in late November 1944, provided detailed testimony about Japanese understanding of American fire control capabilities. The interrogation transcripts, declassified in 1983, reveal the profound psychological impact of technological inferiority. We understood by late 1944 that American gunnery was directed by some form of automated system, Nishino told his interrogators through a translator. The accuracy was too consistent, the salvos too tight, the engagement ranges too long for visual fire control. Our own optical directors, which we had believed were the finest in the world, could not achieve comparable results even under optimal conditions. When American ships engaged in rain or smoke, conditions where our directors were nearly useless, their accuracy remained unchanged. This told us they were not using visual range-finding at all. They were using radar, though we did not understand how radar could provide the precision required for accurate gunfire. Nishino's testimony continued with technical details that demonstrated Japanese efforts to understand American capabilities. We captured documents from USS Houston after her sinking in February 1942 that mentioned radar-controlled anti-aircraft fire, but we dismissed this as propaganda. We assumed radar could provide approximate range and bearing but lacked the precision for accurate fire control. Our own radar experiments had convinced us that radar was useful only for search and initial detection. The idea that radar could replace optical directors seemed absurd. We were wrong. By 1944, American radar was directing gunfire with precision our best optical systems could not match. The interrogation revealed that Japanese naval intelligence had actually identified the Mark 37 director and Mark I, a computer in captured technical manuals as early as 1943, but Japanese leadership had dismissed the threat. The manuals described capabilities that seemed impossible: guns automatically trained and elevated by electrical systems, firing solutions calculated by mechanical computers, radar-directed engagement of targets beyond visual range. Japanese experts assumed the manuals were either propaganda or described experimental systems not deployed operationally. The realization that every American destroyer and cruiser carried these systems as standard equipment came too late to affect Japanese strategy. The Battle of Surigao Strait, on October 25, 1944, provided the final crushing demonstration of American fire control superiority. Vice Admiral Shoji Nishimura's Southern Force, attempting to enter Leyte Gulf through Surigao Strait, steamed directly into a classic crossing of the T executed by Rear Admiral Jesse Oldendorf's 6 battleships. But this was crossing the T with a technological difference. American battleships opened fire at ranges exceeding 20,000 yards, in darkness, using radar-directed fire control. Their shells began falling among Japanese ships before Japanese optical directors could even determine accurate range to the enemy. The battleship Yamashiro, Nishimura's flagship, was hit repeatedly by radar-directed fire from battleships she could not see. The old American battleships, most of them survivors of Pearl Harbor, were equipped with Mark 8 fire control radar integrated with Mark 38 gun directors. The system was less sophisticated than the destroyer Mark 37 and Mark I combination, but still vastly superior to Japanese optical fire control. American battleships achieved hit rates that would have been impossible using visual range-finding at such ranges in darkness. Yamashiro sank at 03:19 hours on October 25, taking Admiral Nishimura with her. The battleship Fuso had exploded and sunk earlier in the engagement after being hit by American destroyer torpedoes. Of Nishimura's 7 ships, only the destroyer Shigure escaped. American losses totaled 0 ships sunk, minimal casualties. The exchange ratio reflected not superior tactics or better seamanship, but overwhelming technological advantage. American ships could engage effectively in conditions where Japanese forces were essentially blind. The psychological impact of Surigao Strait on Japanese naval morale was devastating. Japanese sailors had been taught that battleship engagements would be decided by superior gunnery training and fighting spirit. But at Surigao, Japanese battleships were destroyed before they could effectively engage the enemy. The battle was decided before it began by technological advantages Japanese forces could not counter. Admiral Oldendorf's force achieved what naval strategists called the perfect battle, destroying the enemy while suffering essentially no losses. Technology had made that perfection possible. The captured equipment from Johnston and other American ships sunk during the Philippines campaign underwent intensive analysis throughout late 1944 at Japanese naval technical facilities in Yokosuka, Kure, and Sasebo. Teams of engineers attempted to reverse engineer the fire control computers, but the task proved impossible given Japanese industrial capabilities in late 1944. The precision machining required for the computer's mechanical integrators exceeded Japanese manufacturing tolerances. The electrical servo motors that drove gun mounts required industrial capacity Japan no longer possessed. Most fundamentally, integrating radar with fire control required electronic expertise in receiver design, signal processing, and data transmission that Japanese engineers had never developed. Dr. Tsuneo Rikitake, a physicist assigned to examine captured American radar equipment, would later write in his post-war memoirs about the profound technological gap the examination revealed. When we opened the American radar sets and examined the components, we understood immediately that we were looking at industrial production capabilities, an order of magnitude beyond Japanese capacity. The cavity magnetrons that powered their microwave radar were manufactured to tolerances we could barely measure, let alone replicate. The production quality suggested these were not hand-built prototype units, but mass-produced standard equipment. If the Americans could produce such sophisticated electronics in quantity, while simultaneously fighting a global war, then the disparity in industrial capacity was far greater than we had estimated. Rikitake's analysis extended beyond mere technical examination to strategic implications. The Mark I computer represented approximately 25,000 precision parts, each manufactured to exacting tolerances. To produce one such computer required machine tools, quality control systems, and skilled labor that Japanese industry in 1944 simply did not have. But the Americans were producing these computers by the hundreds, perhaps thousands. They were installing them on every destroyer, every cruiser, as standard equipment. This told us more about American industrial capacity than any intelligence estimate. They could afford to put extremely sophisticated, expensive fire control systems on even their smallest warships. We could not afford to equip our most important battleships with comparable systems. The strategic implications were discussed at the highest levels of Japanese naval command throughout November 1944. Admiral Toyoda convened a series of classified conferences examining whether Japanese naval operations remained viable given American technological superiority. The conclusions were uniformly pessimistic. Without effective radar or automated fire control, Japanese surface ships could not engage American forces on equal terms. Night operations, once Japan's greatest advantage, had become suicide missions against radar-equipped enemies. Torpedo attacks required closing to launch range while under accurate gunfire from enemies who could track Japanese ships continuously. Captain Atsushi Oi, serving on Toyoda's staff as operations officer, drafted a brutally honest assessment dated November 15, 1944. American radar and fire control superiority has negated every tactical advantage Japanese forces previously possessed. Our superior optics are useless when the enemy engages from beyond visual range. Our superior torpedoes are irrelevant when American ships sink our destroyers before they can close to launch range. Our intensive training in night combat provides no advantage when American radar functions equally well in darkness and daylight. Most critically, we have no countermeasures and no means of developing effective countermeasures given current industrial capacity and available technology. The conclusion is inescapable. Japanese surface forces cannot achieve tactical parity with American forces regardless of numerical strength or tactical execution. Technology has rendered our entire surface fleet obsolete. Oi's report was classified top secret and shown only to the most senior naval leadership. The conclusions were too devastating for general distribution. If word spread through the fleet that senior staff officers believed Japanese surface forces were technologically obsolete, morale would collapse completely. The report was filed and never formally distributed, but its conclusions informed Japanese naval strategy for the remainder of the war. Surface operations became increasingly defensive and desperate. The emphasis shifted to kamikaze attacks, submarine operations, and coastal defense. Strategies that avoided direct surface combat, where American technological advantages were overwhelming. The Fletcher-class destroyer production program represented American industrial might at a scale Japanese leadership found difficult to comprehend. Bath Iron Works in Maine, Federal Shipbuilding in New Jersey, Bethlehem Steel's shipyards in California, and multiple other facilities across the United States simultaneously produced destroyers of identical design. The construction time decreased from nearly 2 years for early units to approximately 9 months by late 1944. Quality remained consistently high across all production facilities. Every ship came equipped with the same radar, same fire control computers, same weapons systems, all manufactured to exacting specifications that ensured interchangeability and reliability. Japan's shipbuilding capacity, by contrast, had collapsed under American submarine and air attacks. The destruction of merchant shipping had created critical shortages of raw materials. Bombing had damaged shipyard facilities. Skilled labor had been drafted into military service. By late 1944, Japan was producing perhaps 2 destroyers per month across all shipyards, compared to American production of 15 to 20 destroyers monthly. Even if Japanese ships had possessed technological parity, the numerical disparity would have been overwhelming. Combined with American technological superiority, the situation was hopeless. The examination of captured American equipment also revealed the depth of Anglo-American technological cooperation. The cavity magnetron at the heart of American radar systems was a British invention, transferred to the United States through the Tizard mission in September 1940. The Americans had taken the British invention and mass-produced it with industrial efficiency British factories could not match. The resulting radar systems equipped British and American forces throughout the war, creating integrated Allied technological superiority that neither nation could have achieved alone. Japanese forces had captured British radar equipment in the Pacific Campaign's early months, including sophisticated systems in Singapore and other locations. But Japanese engineers had been unable to reverse engineer the cavity magnetron, lacking both the theoretical understanding of microwave physics and the manufacturing capability to produce the precision components required. The captured equipment sat in laboratories, examined but not understood, while American and British forces deployed tens of thousands of radar sets operationally. The contrast between Allied technological cooperation and Japanese isolation became increasingly apparent during the war's final year. Germany had developed advanced radar and fire control systems, but Nazi-Japanese technological exchange was minimal. The vast distances, different operational requirements, and mutual distrust prevented meaningful cooperation. Japan fought, increasingly alone against enemies who shared technology freely and coordinated research and development across multiple nations. By December 1944, Japanese naval leadership understood that the war was strategically lost, though this understanding could not be publicly acknowledged. The Philippines campaign had demonstrated that American forces possessed overwhelming technological, numerical, and industrial advantages across every dimension of warfare. Japanese surface forces could no longer contest American naval dominance. The home islands would soon face direct invasion, and Japan lacked the means to prevent it. The captured fire control computer from USS Johnston sat in a laboratory at Yokosuka Naval Arsenal through the war's final months, examined repeatedly by Japanese engineers seeking some means of replicating its capabilities. The examination produced detailed technical drawings, comprehensive reports analyzing its operating principles, and recommendations for Japanese fire control improvements. None of it mattered. The industrial capacity required to produce such systems no longer existed. The raw materials were unavailable. The expertise had never been developed. The examination revealed how thoroughly Japan had lost the technological race, but it could not change the outcome. Vice Admiral Fukudome survived the war and would later serve in the post-war Maritime Self-Defense Force. In interviews conducted during the 1960s, he reflected on the moment of realization when examining captured American fire control equipment. We had known intellectually that American industrial capacity exceeded Japanese capacity. We understood that they could produce more ships, more aircraft, more weapons than we could. But examining their fire control systems made the disparity concrete and personal. This was not mass production of simple weapons. This was mass production of extremely sophisticated technology that required precision manufacturing advanced electronics, and integration of multiple complex systems. If they could produce such equipment in quantity for every destroyer, then the industrial gap was not merely numerical, but qualitative. They had moved into a different technological era while we remained trapped in the previous generation. That realization, more than any battle or bombing raid, convinced me that Japan could not win the war. The statistical summary of destroyer engagements in the Pacific from mid-1943 through war's end confirms the decisive impact of American radar and fire control superiority. In night surface engagements where American forces possessed radar and Japanese forces did not, the exchange ratio exceeded 10-1 in America's favor. Japanese forces sank 4 American destroyers in night surface combat from July 1943 through August 1945. American forces sank 47 Japanese destroyers during the same period. The reversal from early war patterns was complete and devastating. The technological transformation of naval warfare that occurred between 1942 and 1945 represents one of the most dramatic revolutions in military history. In less than 3 years, radar and automated fire control changed naval combat from an art form requiring years of training to a science that could be taught to recruits in weeks. The transformation favored the side with superior industrial capacity, scientific expertise, and technological cooperation. Japan, isolated and resource-poor, could not compete in this new form of warfare. The examination of captured American fire control equipment in late 1944 had been an autopsy, not a diagnosis. By the time Japanese engineers understood what American technology had achieved, the strategic outcome was already determined. The Imperial Japanese Navy, which had opened the war with stunning victories achieved through superior training and tactics, ended it, technologically obsolete, unable to contest American control of Pacific waters. The radar and fire control revolution had transformed the ocean that Japan considered its defensive moat into an American highway for invasion. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.